Okay, no slide clicker. So, about me, I am a person. I keep bees. I don't currently have a proper technical job. I've been taking some time off to do a master's degree in human factors and system safety over at Lund University, but I have had a career as a software engineer and then about a dozen years as kind of a site reliability engineer, kind of infrastructure, kind of operations focused person. Having done that, I sincerely now think that everybody who is in software operations should just be issued a beehive when you get your first credentials, because there's something very relaxing, because bees are also a complex system, but at least you can kind of look at it, smell it, see it. It's strangely relaxing after a day of working with computers. So and there's my email address if anyone has any follow-up questions about this talk. So this talk, it's based on some research I have been doing in the past several months, year or so at Lund. This is my master's degree research, and I'm looking at how software operators, typically, or software engineers, are dealing with the kinds of issues and outages. Sometimes these are not acute outages, they're just something that's sort of bubbling away, causing problems, but not taking everything down. So sometimes they're just issues, or sometimes they're big scale outages like this. But when they hit you, and you just do not know what is happening, and you really have to you can't just say, oh, it's this thing that happened Tuesday 2 weeks ago, will kick this service. When you really have to figure out what's going on and what to do about it, and when you have to do this sort of active sense making. So this is a blog post I wrote about that incident on the Slack-Eng blog, if you're interested. So we're kind of dealing with two kinds of classes of things in this research. So we've got both incidents and issues, and I do divide these a little bit. So incidents, something is hard down or really broken, you got a ton of pressure to fix it, like right now, as soon as possible. There's usually a lot of people collaborating, so this will depend on the size of organization you're in. I have seen probably 100 people on a bridge. In a smaller organization, you might not have 100 engineers. But typically, you're working in an environment where there aren't any distractions. There's a whole bunch of people. There's a whole bunch of expertise available and knowledge. And the other thing about these kinds of these outages is you can very often do what's called a generic mitigation. And this is where you are restarting something, or you're upsizing something, or you're draining something, and you can do something to get yourself back. So you don't actually need to understand the causal mechanism. I would say, in probably 90% plus of really significant outages, you can get out using a generic mitigation. The 10% where you can't, and you actually do have to figure out the causal mechanism, think things like, who remembers the big Roblox outage from about 2 years ago? That was one of those where they couldn't solve it using a generic mitigation. So they were down for something like 3 days. But then you have issues. And this is sort of terminology I'll use throughout the talk. Issues where you have time pressure, you don't have so much time pressure. Maybe there's a kind of a core story that we're going to look at through this talk, and this is more of an issue. And because you don't have this acute pressure, you typically have a small team, or maybe just a couple of people, or one person even, that is sort of responsible primarily for looking after and fixing this thing. Sorry, I'm being tech supported live here. Thank you, bearded man. Anyway, so with issues, typically with an issue, they tend to have a different shape. So it tends to be you have this thing, and maybe it's like a little recurring brownout, or something is sort of, maybe 0.5% of your hosts are breaking in some weird way every week. And you just have to figure it out to fix it, because the whole point is that you don't want to generic mitigate and sort of have this thing lurking in your systems forever, right? So in these kind of cases, understanding that causal mechanism of what's happening is the whole thing. Then I also would like to draw a line between two things. These are terms that we often kind of use interchangeably, but I think there is a subtle difference between troubleshooting and debugging. So what I would say is when you're debugging something, oh no. When you're debugging something, we kind of know it's in this piece of code, it's certainly in this binary, it's in this executable, that some problem exists. And so we know kind of where to look. We know we might have to dig a few layers down into libraries or whatever, but we know, generally speaking, it's in this program. Whereas in troubleshooting in a distributed system kind of infrastructure context, you don't necessarily know where to look. It could be in any one of a bunch of different kind of services or executables, or it could even be in some weird interaction between two parts of the system, or more than two parts of the system, because this is one of the kind of core characteristics of complex systems, in that a lot of the times the problem isn't really here or here, it's in the whole thing. So what we're looking at here is more along the lines of troubleshooting rather than debugging. So troubleshooting scenarios, I mean, I'm guessing many of you do this work routinely. Hands up if you do troubleshooting as part of your job. Effectively, almost all of you, right, yeah. So always something like this. Something is broken, or it's doing something that someone doesn't want it to do, or it's slow, or it's intermittently broken or slow. Very common, very annoying, always very annoying. Or some subset of the thing is broken or slow, or maybe it's using too much of some resource or something. Or something else, but usually it's one of those first few things. So I'm going to tell a troubleshooting story, and then we're going to kind of look at it through some of the cognitive psychology lenses that I have been using to analyze these things. So our story begins, it's a small organization. This organization has something like 10 technical staff. They have a 2-person DevOps team at the time of this incident, and they have several devs. And they're a JavaScript and a Java house, and they're running on one of the big cloud providers, and it makes no difference which one it is. So our story begins, as so many stories do. Customers start to notice performance problems, and they start to complain. So what they specifically are saying is that the kind of core API seems to be kind of browning out, so it's getting slow or flaky every so often for a little while, and then it comes back. So, given that this is sort of it's a very fuzzy issue, it seems to be, there's no sort of specific thing they can point at, like a piece of broken code. It lands with the DevOps team. And this is really common as a pattern. So in a lot of organizations, if there's any sorts of performance issues or flakiness, it very often lands with a DevOps or infrastructure or SRE or whatever we're calling it this week, or a sysadmin team, right? And so they spend some time, and they eventually, after clicking around a bunch of consoles, they notice that the API service has been going unhealthy, and then it's getting restarted by the orchestration system after some time. And this is happening kind of most days around peak time. This had actually started a couple of months ago, and they hadn't noticed it internally because they didn't have a lot of monitoring for this kind of stuff, but it was ongoing. And so this, again, is a small organization. They're not super operationally mature, and they don't have a lot in the way of metrics. They don't have kind of distributed tracing or any fancy newfangled stuff. They have logs, because it's always logs. This is another thing that fell out of the research that I'm doing. Despite all the fancy observability stuff that people will tell you about, and it is genuinely great and really cool, people are still using logs most of the time for most of their troubleshooting. This is what I see when I ask people. But in this case, the logs are not showing anything interesting. But what they do know is, they know that the only thing that this API service depends on externally is the database. So it must be the database, right? What else can it be? It doesn't depend on anything else. But it is a red herring. But the reason that they're looking at the database is partly because, like I say, it's the only dependency, but they already had a lot of suspicion around the database. In the months leading up to this, they had already been kind of concerned about database performance and whether some of their queries were slow and inefficient. So it was kind of top of their mind already. So they kind of went, great, we'll hire a consultant, we'll optimize some queries and index, indexes, and they also upscaled their database, like as a generic mitigation. Can we fix this for now by upscaling the database until our consultant sprinkles his magic indexes or whatever over it and it makes everything better. But upscaling the database changed nothing. Ooh, that's a clue. And they're looking at the database metrics as well. It's all very quiet. There's no actual evidence of database sort of resource contention or any kind of performance issues there that they can see. So a red herring maybe. So here's another red herring. They decide that since maybe it isn't the database, maybe we changed something around the time that this problem started to happen. So it turns out that they had moved from running it on a VM. Sorry, I think I'm getting troubleshot again. But I'll continue telling the story. They had been running this application directly on a VM, but they moved it to a managed container service around the time that the problem started. Now, they can think of no reason why this could have caused the issue, but maybe it's the problem. So they kind of go, should we revert back? But it's 3 months later, and a lot has changed underneath the hood, and it's a bit of work to revert back. So now they're kind of at this crossroads. They're saying, well, we don't know what the causal mechanism is at this point. Should we revert back to trying to run directly on a VM? Should we like double down on the database optimization stuff, or should we add more observability to see what's going on, or do something else? So this is several months on from when this started, and several weeks at this point from when they first noticed the issue. They have been at this weeks, and they do not know how to move forward effectively, and they're kind of stuck making this decision. They have some theories about some possible causes. They don't have any really strong evidence as to which it might be. All they really know at this stage still is that their API is periodically freezing and getting restarted, and it's causing customer pain. And one of the kind of factors that's going on here is that DevOps are still the ones that are owning this issue, despite the fact it's clearly something to do with this API service, and the back-end Java developers are not getting involved whatsoever. So how do they get unstuck? So they got unstuck, and an external engineer joined this effort. Somebody who didn't know anything about this specific service, but who had done an awful lot of Java performance work. And they kind of go, well, maybe this sort of first principles idea that it's something external to the application, that may be wrong. Because sometimes applications run out of their own internal resources, right? And also, this person kind of went, well, based on their kind of experience, and they had an intuition that usually if a database is slow, your application will be slow, but it won't kind of freeze in that way that causes it to fail health checks and get restarted. It will just be slower. And the advice was that the DevOps team should try and work on getting some Java thread dumps occurring during the application freeze so that you can see what the application is doing. So now we're moving into this mode where we're focused on actually gathering data so that we can get some hard evidence about what's causing these symptoms. And this is a very simple story. This is not a very complicated outage story, but it's a real-world story that we can learn some things from. Okay, so at this point, we're getting towards getting unstuck. So the DevOps engineer in the organization read the thread dump and thought it meant that the application had run out of threads and should increase its thread pool size. But the external engineer looks at it and says, okay, actually what we can see here is your threads are all waiting for a database connection from the database connection pool. So the external engineer knows what a database connection pool is and said, okay, well, looks at the database metrics, says, we seem to be bottlenecked on database connections. We can see that we don't have many connections inbound. This seems to be the problem. It all lines up, and increasing the connection pool count fixes the problem. So, yay, okay. So what can we learn from this story? We can learn a lot from this story about how troubleshooting works. So this is how I've been doing this research. I've gotten about 16 cases, of which this is one. And for each of them, I've been sort of representing them in this kind of way. This is a process trace that sort of shows what's happening in this story. with sort of different kinds of events. So when people are coming up with different hypotheses, when they're stuck, and when they're seeing cues or observations, when they're taking actions or events, and when they're sort of experiencing uncertainty or conflict. And so from this, I've been using this sort of format to make comparisons between different cases and see what sort of common things we can see. So here are some of my takeaways from this case, and that's that expertise seems to matter. And I think this will probably resonate with a lot of people. I think probably most of you will have seen that it's much harder for a novice to make sense of troubleshooting than it is for somebody who has seen these things before. So an expert can very often do this stuff very quickly in cases that have stumped other people with less expertise or less relevant experience for a long period of time. It's also very easy to spend a lot of time chasing red herrings. So I think what's quite important, and this is very difficult to do, what's quite important is if you're going to spend a lot of effort going down, investigating or trying to fix something, it's useful to actually think about what hard evidence do you have that this is actually the causal mechanism of whatever you're experiencing, rather than sort of spending a lot of time down a red herring. So that's why in this case the pivotal moment is really saying, okay, we'll get these thread dumps and actually see, rather than trying to theorize from what limited data we have, trying to actually see into the application to see what it is waiting for. That's your hard evidence that tells you what you should be doing next. Troubleshooting cases, they often do have a lot of uncertainty. So, I'll show you here. So even here, kind of at the top left, we have some sort of stuff about what they were doing early on in the case. So, they really did think that they had a lot of database problems. That was what was pointing them there. But then uncertainty kind of arises when they upscale that database and they don't see any improvements. That's when they start thinking, well, could it also be this VM issue? So they have all this sort of these quite unclear clues, and that's where they get stuck. They get stuck in that uncertainty, and they don't have the tools to resolve that. One of the things I think is most interesting is in troubleshooting, you very often actively have to gather data that you can't get kind of passively through looking at logs or metrics. So you may have to look, you can't always solve it with your dashboards and your logs. Sometimes you might have to add additional log lines. Sometimes you might have to start making graphs of metrics that are not in your dashboards already. And sometimes you'll have to use these kinds of introspection tools, like attaching debuggers, doing profiling, all this kind of stuff, particularly where it's performance related, because that's one of the things that shows up very poorly in logs. And then when you go to interpret the data, you have to have or be able to build a mental model of what's happening in the system. So in this case, even when we get to the end of the case, and one of the DevOps engineer who doesn't know about connection pools has this incorrect mental model that is about threads. So even at that point, you can sort of interpret the data incorrectly. So a mental model is absolutely essential to interpretation of data. One of the really interesting, we'll go into this a little bit in some of the coming slides, is that we all have incomplete mental models of our systems because they're changing all the time and they're just too complicated to have a full mental model of every single layer of abstraction. We just do not know it. I guarantee you, for every single one of you, there is some fairly important part of your system that you do not even know exists. And this comes up repeatedly in troubleshooting cases. People find problems in parts of the systems they did not even know were there. So this is a phenomenon that happens when you get to the end of a troubleshooting case. You only really know for sure that your final confirmation that you've solved it is always you do something and it fixes the problem. But there's a phenomenon that happens when you join the dots. You create that mental model of the situation and why the breakage is occurring, and it all sort of aligns. You go, okay, I am very sure that is it. I think many of you will probably have experienced this. So when you experience this, it's a pretty strong sign that you're on the right track. Although, like I say, you still got to test it. So I think troubleshooting is one of the hardest things that we do in distributed systems. And there's a bunch of reasons. So intransparency is a big problem. We cannot observe the internals of our digital systems directly, unlike my beehives, which is why that's so relaxing. We have to rely on logging, metrics, tracing, kind of stuff that we've already engineered in so that we can observe. Or we have to be able to use introspection tools. And it's surprising how often people are, or how infrequently people are like reaching for introspection tools like debuggers, like profilers, like thread dumps. In my research, I talked to a lot of people about what tools they're using to solve their problems or to address these kinds of problems. And in many cases, people report that being able to access those tools like packet captures and debugging and so forth is difficult because increasingly there are security restrictions that make it very difficult to do this. And this is something I've also seen in my own career. So you may have quite a lot of hoops to jump through to even get to the point where you can do active introspection onto your system. And then sometimes modern orchestration can make it harder as well because you don't have this sort of broken instance that's just sitting there. If something breaks, it's generally killed pretty quickly these days, which is great for the stability of our systems, but also very bad as a troubleshooting step. So we have a few challenges there. And then, like I said before, just understanding what you're seeing can sometimes be a bit of a challenge because you need to go and find out what things mean, build that mental model to interpret the observations. So logs are a double-edged sword in troubleshooting. You can do a lot with logs and they can give you a lot of flexibility and a lot of insight into what's happening. They're very searchable, they're very accessible, you don't need a lot of specific expertise, and they work great in a lot of cases. But for the most difficult cases that you see, particularly where it's around performance, it can be a poor fit. One of the big problems is, in this particular case that we looked at, we have requests that are coming in. They start to wait for a database connection, and then they're waiting for an indefinite period of time, and then eventually the instance gets killed. That means there's never a log line for those requests because you log typically on completion. So that performance problem is completely invisible in logs. You need some other way to see it. Logs are also very messy and noisy. Any log for any sort of system that's been around for a little while, it's always going to be kind of cluttered up with random warnings, maybe some errors, all sorts of weird stuff. And that means there's a great potential to go down any number of wrong paths, investigating red herrings. And that's really a kind of considerable risk with logs as well. Log volume can be really overwhelming. One of the cases I looked at was somebody was trying to solve a weird networking issue in a bespoke networking appliance, and one of the big problems they had was their only real way to inspect this thing was through logs. They were interested in a particular service, but they had no way to set the log level for that service to be high, whereas keep the rest of them to be minimal. So they were just churning out logs and logs and logs from all these services, and to the extent that it was difficult to actually export them from the appliance to be looked at. So some of the infrastructure around logs can be a problem as well. I had another case as well where engineers spent months trying to track down a problem, and which was intermittently occurring in their fleet. And at the end of it, they found that actually there was a log line that would have pointed them pretty directly to it, except they had the log level set in such a way that that log line was not being exported. So, yeah. Now, there's a weird little organizational quirk that I see not in a majority, but in a minority of cases, where management get very, very convinced that a problem lies in a particular part of the system or in a particular direction, and they direct the engineering team to go and look into that. Now, the problem here is the management are typically way more hands-off. They probably don't know. They're just, they're pattern matching on something they've seen before. But the effect of this on staff tends to be that the staff will feel that they have to absolutely, exhaustively disprove this theory of management. And it can be really time consuming. So it can be a big waste of time. I really recommend that management avoid doing this if they at all can. So uncertainty, we talked about this a little bit. Troubleshooting is it's nothing but resolving uncertainty, really. What is the problem? How much impact is there? When's it going to be resolved? How much work will it take? You know, what's causing it? Is it this or this? Should we spend time investigating that or that? Nobody likes uncertainty. It's kind of human nature. We like certainty. We like to know what's happening. But when we're troubleshooting, we have to live in this world of tolerating uncertainty and keeping an open mind. Because when we prematurely dismiss or prematurely commit to certain paths in troubleshooting, that is when it's one of the ways that we go wrong. And like I said this before, we don't know what we don't know. We have unknown chunks of code or configuration in our systems, and we don't even know they're there. In this case, the DevOps team didn't know that the configuration pool was there, and I don't think the application team knew either, because somebody had added it in 6 years previously. They'd left it at the default configuration, so there was no configuration file for it even. And then that person left. And then for however many, 5 or 6 years, this organization did absolutely fine on the default configuration, and then it blew up. And they didn't know it was there. It was a total unknown quantity. And it's partly because of the intransparency. You can't see it because it doesn't show up anywhere. If you don't have a monitoring dashboard for it, or a runbook, or a configuration file, it's very easy to forget that something even exists until it breaks. Okay, so I added some extra parts about configuration because of the theme of this conference. Configuration issues, I wouldn't say that they're the number one kind of cause of very difficult to troubleshoot issues, but they were a major factor in 6 of my 14 cases that I analyzed in depth. So that's quite a substantial chunk of cases. So I mentioned again, intransparency, kind of not being able to see into things. I find the configuration often affects things in ways that you can't observe directly. You can kind of see the side effects of what the configuration is doing. So I've got a couple of cases that dealt with things like, how many processes should be running a particular Java runtime, particular language runtime, wasn't Java in this case, or things about preemption, that kind of stuff, networking configuration. You can see the effects of what these things are doing, but there's no direct observable link to whatever the configuration setting is. So as a troubleshooter, you have to observe the symptom, connect that to potential configuration stuff. And if you don't know what that particular piece of configuration exists and what it does, now you've got a kind of a discovery problem, right? So config is all kind of often off to the side. There's a weird ownership thing, and this is particularly true of things like application configuration, which stuff like the database connection pool in this instance, and also language runtimes. So developers typically kind of say, we own the code, so they may not think that they own the application configuration stuff, and particularly the language configuration stuff. And then you'll often have an infrastructure or an operations team that say, we own the databases and the load balancers and the orchestration. And you have this little layer of application and language runtime configuration that sits between those things. And it's no man's land. And nobody thinks about it, nobody looks at it on the regular. It's kind of a problem. Defaults. Defaults are invisible. You don't have to write them down anywhere in your code or in your configuration. They're just happening. And that makes them even more invisible than configuration is in general. They make discovery of this configuration setting existing. They make it hard. Config documentation is not always the best. I think a really good practice that can be used to combat this a little bit, every application, in my ideal world, every application would have an endpoint where you would list its configuration settings and what they are live, obviously not including secrets. So DevOps teams. DevOps teams as the owner of last resort of all kinds of problems. this can be an issue. And I saw this in a few of my cases where it was a real issue, where this kind of infra-focused team is just dumped with all problems on the basis, well, performance things, it's always infra. And if the problem actually lies in the application, it can add a lot of extra time to the troubleshooting step, because very often those DevOps teams will need they'll need some developer support to do the introspection stuff or sort of make sense of what's happening in the application. I had several cases where, where teams just got stuck until they got more developer support. So there's a phenomenon that I've noticed. This happens in a majority of my cases. There was what I would call like a go-to troubleshooter. So somebody who sort of makes a point of running towards the fire and gets involved in a lot of troubleshooting cases and just has a lot of experience and expertise in this. Nearly every organization has one or two of these, sometimes more depending on the size. And these are sort of, looking at the faces here, I see a few faces like the faces I was talking to in my study. People who came up through sort of, in the 90s, running your own infrastructure, on bare metal. We have a different world now where, you have young people coming up through, and they'll spend their whole life, their whole working life will be in Docker and Kube, and you're never getting down to. You're never getting down to broken stuff on bare metal level, and that's fine. It's productive work. It's productive infrastructure on these tools, but when things break, you're sort of left not knowing how to get through the different layers of whatever is broken. So I think that organizations should be thinking about staffing levels and sort of thinking about this sort of phenomenon of centralized troubleshooting expertise and how they can foster building troubleshooting expertise more broadly, and maybe thinking about formalizing that sort of troubleshooter role in a way. And just because somebody has a DevOps or SRE title doesn't necessarily make them a great troubleshooter. Lots of us are not. It's kind of a causality thing here. So the root of troubleshooting is sort of determining what is the causal mechanism of something that is broken in a way. The tools that we have are geared towards showing us state, typically. What is the state of this metric? Did this log line occur? Figuring out how the system got into that state is often a very big part of doing what we're doing. And this requires sort of a synthesis of what you know about a system with what you're seeing. And that's hard cognitive work. So that's one of the big problems that we have. And I think distributed tracing and some things like that do help a little bit, but they're not the whole story. So we have quite a impoverished tool set, and that leaves a lot of work on us. So looking at the cognitive science research, there is very little research directly about digital troubleshooting or troubleshooting in digital systems. There's research about troubleshooting in other domains. This is some very old research by Jens Rasmussen that he did with nuclear power plant operators. So he thinks that there are three levels of sort of skill, rules, and knowledge that you use when you're responding to a system event. So skill-based behavior is, you see something, you do something. So in our world, you get paged, you act the page, right? It's not very much thinking to it. You might follow then the next one is rule-based behavior. So maybe you're following a rule book. It says, when you get paged for this, go and run this command and see what it says. Knowledge is really where we're at when we get into troubleshooting troubleshooting novel things. So we have to understand what we're seeing, we have to make some decisions about it, we have to think about our goals, and we have to make a plan. But Rasmussen only really takes us so far. The next researcher of note is Gary Klein. He is a psychologist. He did a lot of work on how firefighters and other sort of people in these high pressure situations think about the situations they're in and how they make decisions. And he also looked at doctors and lots of other professions as well. He has this theory of recognition prime decision making, where you kind of pattern match your current situation to things you've seen in the past. This tells you kind of what reasonable courses of action could be. Then you do a mental simulation process to evaluate what you think might happen if you take various kinds of courses of action. Like, will it work? Will it have undesirable side effects? And I think this is something that we certainly do a lot when we're faced with broken software. One of the things that Klein sort of underlines is that this happens even when we're not seeing situations that are the same exactly as previous situations. So this happens when we can pattern match on just elements of situations. So in the case that we looked at before, our Java engineer who came in to help solve the problem, they hadn't seen this particular application doing anything before. It was a new application to them. But they had seen frozen applications before, and for them, doing that thread dump was a big part of, was basically sort of just their intuitive response to that. Then there are limits about doing mental simulations. And like, as a human being, you can only sort of move so many blocks in your brain at a time. You can simulate about 3 different things moving in a system in your brain. Now, I think most of us probably have a lot more than 3 parts in our systems, right? So we have a problem here immediately. Certainly depending on what level of granularity you're looking at. So one of the things that you can do is if you're well experienced with a given system and you know it very well and you've seen it do a lot of stuff, you can use a thing called chunking, where you can basically say, okay, well, I will treat this whole, part of a system as one thing, a chunk, and that then is one of your 3 parts of your system. So you can use this chunking phenomenon to get a lot further with your mental simulation of systems than you can as a novice who has to think about every piece individually. So this comes from Dietrich Dorner's work. He's another psychologist. Experts also process information differently. This is Dorner again. Instead of seeing individual signals and having to puzzle everything out individually, Dorner thinks that experts are using a thing called super signals, where you look at how a bunch of different signals are moving together. So think about, say, I think many of us are probably running web applications. If you start seeing, the number of incoming requests going up and your number of in-progress requests going up and your latency going up, what you know that you probably have an overload problem, or maybe you're getting a bunch of retries. So you've seen that pattern before. That's a super signal to you. So I think the most fundamental thing for my research was Klein's data frame theory of sense making. So this is the same Gary Klein who did the research on the firefighters and the mental simulation. So a data frame is a bit of a weird idea. So Klein thinks it is it's a story or a map or a plan. He says it's a way to relate different aspects of a system together with a sort of a narrative or a story. So in our system, or our story that we've had here, when we start off, the engineers involved, the DevOps team, they have this sort of data frame that says, well, it's most likely the database, because the database is the only dependency. And that's their data frame, right? Their data frame is influenced by a bunch of stuff related to previous issues they'd had with the database being slow. And this is why, and that guides the search for more information. So because they have this data frame that it's the database, they're looking at database performance metrics, they're looking at slow queries, they're looking at all this database related stuff. Data frames anchor on a small set of data. And data in this case doesn't have to be like on a graph or like a metric or a log line. Data can be what you know about the system. So in this case, the data in question is this team, which had this idea that they had database problems going on, and that's their anchor, that and the fact that it's the only dependency. So data frames are really important in troubleshooting because we always have a data frame. There's no sort of cognitive vacuum, right? And even if you've just been paged, that page that you get, that's your data frame. Like that, and whatever if you've had that page before, what was that page the last 2 times you saw it? That's your data frame. You're coming in and you've got some ideas already. People who have been around longer, who have more experience, who have more expertise, they have a richer set of frames. And this is one of the big reasons why experts can often solve problems efficiently where novices get stuck. Because the novices do not have the frames. They don't have a good frame for the situation, so they have to work a lot harder to get to the same place. It's not their fault, they just haven't seen it. So an interesting implication from this is there's kind of no shortcut. You can't just magically give somebody a process and say, follow this process and you will be an excellent software troubleshooter. Because you also have to have seen some shit. So, to me, then, the implication of that is it's really important in organizations that we give people the opportunity to see some shit. So, I think most of us, it's my experience that organizations always have a few weird gremlins floating around in the systems. I actually think if we want to be prepared for major outages and we want our staff to be good troubleshooters, I actually think it's a reasonable use of engineering time to give people practice of troubleshooting by assigning them to hunt down some of those gremlins some of the time. So that's my take on it. Sense making, sometimes you have to hold multiple frames. This is one of the ways that we deal with uncertainty, right? So if we don't know if we don't know whether it's the load balancer or whether it's the application, we have to kind of simultaneously hold, might be the load balancer, might be the application frames. And they guide us to go and find what metrics or what other data we need to determine which of those issues it is. We do that differential diagnosis. So, I mean, for me, if you say, hey, Laura, this service A can't talk to service B, I immediately have about a dozen frames. I'm saying, well, is it DNS? Of course it's DNS. But it could be service discovery issues, it could be socket exhaustion, it could be file descriptors, it could be a whole bunch of stuff, right? And so I don't know which it is. Like I've got this of frames, but you go and you try and eliminate a bunch of stuff to get down to what it is. So this is kind of how I see data frames working in a troubleshooting kind of context. So up the top left here, we have our data frame, and we always have a data frame, and we're always elaborating and working on and modifying our data frame. And then we're anchoring that on data. We're gathering more data based on it, and we're using that to sort of update our mental model of how the system works, which we can then use to do mental simulation and make predictions about system behavior. So this is, for me, kind of how the cognitive science of it hangs together. Like when we build a good enough mental model, we can kind of simulate the mechanism of the failure and fix it. So we'll skip over this for time reasons. Let's skip this. We talked about that. So, and this again is another sort of way of looking at the software troubleshooting process. So we're always, like I say, we're coming in, there's an initial data frame based on the whatever report or page or whatever we got. We got our initial knowledge of the system, our previous experiences, and then either one of two things happens. You can either have sort of a very clear place to look based on all that, like maybe it all points to the message queue consumer being wrong, for example, or if not, you're just going to sort of start scanning your dashboard, scanning your logs to see if something pops out at you that looks strange. And that's how we do it. I'm going to quickly run through this. There are maladaptive and adaptive troubleshooting modes. This comes from research by Jenny Rudolph, which she did mostly with doctors and medics, but I think it totally applies here. So the stalled troubleshooting process is where you can't think of what to look for. You just get stuck. You don't know, you've gotten this problem or this report has come in and you just do not know where to look. You've scanned through logs or dashboards and nothing is weird. You're out of ideas. The second one is fixated. This is kind of what we saw in this case that we looked at. You decide that the problem is in some specific area, and it isn't in that area, but you've kind of gone down that path, and you need to jump back up and start your search from somewhere else. That's how you get out of fixation. Thematic vagabonding is where you're pinging around a bunch of different areas, but you're not spending enough time on any one to rule it in conclusively or rule it out. So you're just sort of you're kind of thrashing, right? You don't get there. I added a diagnostic mode to Jenny Rudolph's 4 modes. I've added the shut out mode, which is, I think, something that I'm seeing in computing, where people have ideas, they have things they'd like to be looking into, but they cannot get the data and usually because you're shut out. Either the platform doesn't allow you to see what you need to see. It's too much of a black box. So those are 4 diagnostic modes that do not work. The one that works is troubleshooting as a search. We view it as a search. This is not my idea. This is David Wood's idea from the Stellar report in 2017. But the troubleshooting in process, you generate a bunch of places that you would like to look. You investigate, you rule out an area, you look into the next area, and you find the causal model of the issue through gathering data, building your mental model, running your mental simulations, finding something that matches the symptoms. So, how to troubleshoot the worst issue of your career. You may need to build some new models of your system. You might need to look beyond logs and beyond metrics. You may be dealing with things you don't know existed. You have to treat it like a search for answers and be principled about your search. Don't spend too long fixated on something that is not the right answer. Don't diagnostic vagabond. Treat it as a search, rule an area in or out, move on to the next. You will get there eventually. All issues are troubleshootable. It does take time and persistence. It might take asking for help. It might take learning a new tool. But when you get to the other side, you will have a richer set of frames and you will be a better troubleshooter. And the next time it may get easier, or maybe it won't. Maybe you still won't have a frame. So I used a bunch of sources in this talk. They are here. I have put these slides up on requisitevariety.net, my terrible 1990s style website. And yes, thank you very much.